Yes?
I eat up my chicken.
No.
Well, that starts to become a hassle for me because I need time to like heat up my food. But yeah, sure, if it's just
It'll be like a minute.
Okay. Okay, we're ready? Is it turned on? Alrighty. Hey, you guys. Today we're going to learn about tension. You ready? Yes, the feeling you feel before every one of my exams. Tension. Here we go. Hand. Yo-yo. Tell me, what's holding up the yo-yo?
A string.
Thank you, the string. The string is holding up the yo-yo. And when a string exerts a force, we call that force by tension. Well, we call the force by the name tension. We call it tension because a string must be in tension. That is, the string must be taut in order to exert a force. Let me show you. Here's yo-yo. I can exert a force. I can pull the yo-yo toward me. Can I push the yo-yo in the opposite direction? No. Nothing happens, right? Because tension only works in tension. Tension only works when the string is taut. Alrighty? And so that's the first thing I need to define for you what tension is. Here it comes. Tension. Force exerted by string or rope or wire, etc. Anything where it has to be taut in order for it to exert a force. A wood 2x4 is not an example of tension because although, yeah, you can attach something to the end of the wood 2x4 and pull on it and move it, you could also push it with that wood 2x4. The 2x4 doesn't have to be in tension to exert the force. It's solid. So tension only applies to things that have to be taut. Okay, great. Next, the microscopic understanding of tension. Here's my string. Here's a 10 Newton mass, or a 10 Newton weight, okay? What's holding up this 10 Newton weight is tension, tension. So if I were to make a free body diagram, I'd go like this, 10 Newtons for the weight, and then the force that's opposing that 10 Newton weight is tension, the force exerted by the string. But I want to go microscopic now. Consider this weight is not being held up by the entire string. This weight is actually being held up by the molecule that's in contact with the weight. By this guy. This black molecule is holding up that 10 Newton weight. So if I did a free body diagram of that black molecule, then that weight is pulling down on it with a force of 10 newtons. I know the weight is pulling down on that black molecule with a force of 10 newtons because that black molecule is pulling up on the weight with a force of 10 newtons. You see? And so by Newton's third law of motion, if this black molecule is opposing the 10 Newton weight of that weight by pulling up on it, then that weight must be pulling down on that molecule with 10 newtons of force. So looking at this black molecule, I'm pulling down on it. This guy's pulling down on it with a force of 10 newtons, but this black molecule is not accelerating towards the center of the Earth. There must be an equal and opposite force being exerted on this black molecule. What's exerting that equal and opposite force on this black molecule? What's that, Noah? Good, tension. But specifically, who's doing it? Hey, I'll tell you. The molecule directly above him. He's pulling up on this guy with 10 newtons of force, right? The green molecule is exerting a 10 newtons of force up on the black molecule. Well, let's go ahead and do a free body diagram of the green molecule, okay? Here's my free body diagram of the green molecule, and because the green molecule is exerting 10 newtons up on the black molecule must be exerting 10 newtons down on the green molecule. But the green molecule isn't accelerating towards the center of the Earth. Who's exerting 10 newtons up on the green molecule?
The blue.
Another molecule? The blue molecule? You see what I mean? So the blue molecule is exerting a force, 10 Newton force up on the green molecule and up the line, right? I want you to see that every molecule in this string is getting 10 newtons of force down on it and 10 newtons of force up on it. That's what it means for the tension to be equal to 10 newtons. Not only does it mean, hey, that rope is holding up a 10 newton weight, what it really means is every molecule in that string is feeling 10 newtons down and 10 newtons up. It's in tension. I'm exerting a force on both sides, in both directions. And that force is what the tension on the string is. So let me write that down. The tension value tells how much force is being exerted on each molecule. And I'm using the term molecule, but I'm going to show you momentarily. There's not really each molecule, but each whatever. How much force is being exerted on each molecule in opposite directions. Now I want to show you it doesn't have to be a molecule. I mean, if you look at a string and the string has some thickness, okay, then you can kind of think of it as each band of the string. This band is exerting a force up of 10 newtons, which means there's a force down of 10 newtons on it, which means the band above it is exerting 10 newtons of force, and so on. However you want to think of it, molecule by molecule, band by band, clump by clump, whatever, each one of those guys is feeling 10 newtons up and 10 newtons down if it's under 10 newtons of tension. Let me give you a kind of a visual example of that. Here. Okay, let me get this out. This is a 10 Newton weight, okay? I am now going to hook it on this spring scale, alrighty? The spring scale is holding up this 10 Newton weight. Spring scale is exerting 10 Newtons force up on this 10 Newton weight, which means the 10 Newton weight is exerting a force down on the spring scale of 10 Newtons. Well, the spring scale is getting a force down of 10 Newtons because of this weight, but the spring scale is not accelerating to the center of the earth. Why not? What's exerting the equal and opposite force to the 10 Newtons down on the spring scale? What's exerting the 10 newtons on this spring scale that opposes the 10 newtons of the weight? Yes? Yeah, my hand, right? My hand is. And I want you to see that's the way tension works. This spring scale, that's the way spring scales work. Spring scales don't work because you're exerting 10 newtons down on it. They work because you're exerting 10 newtons down and 10 newtons up. Then your spring scale works. If all I had was 10 newtons down, it wouldn't be a spring scale. It would just be accelerating to the center of the earth. You see? So this is an example of tension. There's 10 newtons tension on the spring scale. Well, hey, let's talk more about tension. Alrighty. Here's my scale. All right, it's a little bit off, but whatever. Okay. Here's a approximately 10 Newton weight. So what's the tension in the string? 10 newtons, right? It's 10 newtons because it's holding up 10 newtons of stuff.
Yeah.
You guys okay with that?
Yeah.
Let me ask you this question. What if I decided to hold up my 10 Newton weight with two separate and distinct strings? Now, what would the tension at each of these strings be? How many people vote 5 newtons? Hey, good for you. You're right. It would be 5 newtons. That makes sense, right? But let me ask you this. What if I took this string, here just a second. Oops. I was only a couple inches tall. There we go. Okay. What if I do this? Oops. What if I have one continuous piece of string and I just cradle the mass in the middle? That is, I don't have two separate and distinct strings, which are obviously each going to exert 5 newtons to hold up that 10 newton weight. Instead, I just have one continuous piece of string, and then I hang the 10 newton weight off of that continuous piece of string. Is it still going to be 5 and 5, or is it going to be 10 and 10? Please think about it for a second, then we'll have a vote. I need to drink water. Okay. How many people say it'll be 5 and 5? A couple of you. How many people say it's going to be 10 and 10? Several of you. Hey, I'm not even going to try to convince you of anything. I'm just going to do it. Here it comes. You ready? What did it end up being?
What?
5. I mean, it's a little bit off kilter. Here, just a second. Okay, there we go. You guys okay that it's 5 and 5? I'm doing this to show you it doesn't matter if it's two separate and distinct pieces of string or one continuous piece of string that you're hanging something from the bottom of. This and this are the same situation. This is no different than that. So don't be thinking that this is any different from that. So I got my 5 newtons per, okay? But let's say you hung a sign from a ceiling and it wasn't exactly vertical 5 and 5. Let me give you a scenario. This is example number 1. Okay? Suppose this is a 60-degree angle and I'm hanging a 10 newton weight off of 2 wires that are attached to the roof, and those wires make a 60-degree angle. I'm going to find the tension in those 2 wires. That's the problem. Find the tension. And are you okay that we call tension by the letter T? I don't know if I actually said that anywhere, but we call tension by the capital letter T. Well, this is a pretty weird problem. What would you have me do first? What do you think, Imani? What do you guys think? What should I do first? Yes, Maxwell?
Draw a line between the 2 tensions.
No, don't do that. What do I do first? Yes, Logan?
Free body diagram.
Thank you very much. Please draw your free body diagram. That always comes first. Then we'll do what Maxwell was saying. But first, do a free body diagram. Okay? Do a free body diagram on this weight here. And actually, I drew it so that it's a little fake outy. Let me make it less fake outy. Let's just pretend that both strings are attached directly to the weight, even though it'd be no different if they were attached together and then the weight hung down. It'd be the same thing. But let's go ahead and just do it like that so it fakes you out less. You guys okay that I've got 10 newtons down, I've got tension this way, and I've got tension that way. And there's my free body diagram. Next, I'm going to do what Maxwell was recommending. I'm going to say that this is a 30-degree angle and this is a 30-degree angle. I'm going to define up as positive and to the right as positive. So go ahead and make your free body diagram. And now here comes the next part. Whenever you have a force at a weird angle, you know you want to get x and y components of them. But think about that problem we did yesterday with the helicopter. Did I do the helicopter problem with you guys yesterday? Okay, what did I end up doing to the lift that was a weird angle, but I didn't know what the lift was? Yeah, I just did x and y components of the lift. I did L sub x and L sub y. Well, I'm going to do the same thing here. I'm going to have a y component and an x component of tension, T sub x, T sub y. For this tension is also exerting a y component, T sub y, and an x component, T sub x. So go ahead and draw on your x and y components for your tension. So now what would you have me do? Some of the forces in the x direction or some of the forces in the y direction?
Y.
Y.
Why?
Why, Justin, why do you choose the Y?
Because we know the force going down.
Good, because you know the force going down, you know that 10. In fact, doing some of the forces in the x direction isn't going to do me much good. I'll get t sub x minus t sub x equals 0. Well, okay, but that doesn't really help me. So let's go ahead and do some of the forces in the x direction. I'm sorry, in the y direction. Equals MAY. I got the y component of tension due to this guy. I got the y component of tension due to that guy. I've got the 10 newtons going down. What's the acceleration of this sign?
So,
Yeah, why?
that's not going anywhere.
Thank you, because it's not going anywhere. It's remaining at rest. Not only is it at rest, but it'll remain at rest. So you guys okay that I got Ty equals 5 newtons? The y component of tension has to be 5 newtons for each of these strings. Do you notice that's the same as these tensions? Each of these tensions was 5. Well, each of these y components have to be 5. Well, let's go ahead and find t. I got the cosine of 30 degrees equals t sub y over t, or t equals 5 newtons over the cosine of 30 degrees, which ends up equaling about 5.8 newtons, I think it is. So I found the tension, 5.8 newtons. Why is this tension greater than 5? All I need is 5 newtons for each string to hold it up. Why is this greater than 5? Yes?
Because it's at an angle, so it has to be able to hold up more in order to support that angle as well.
Yeah, that's a good way of putting it. Great. Or the fact that now I've got this x component of tension, a component that does me no good. All it's doing is working against that x component, but it's still there. So the total tension is going to be more than the 5. Yeah. Okay, here's the problem I want you guys to do. Now, I have a 10 Newton sine that's being held up by 2 strings. And these 2 strings have a 150-degree angle between them. Please do a free body diagram and some of the forces in the y direction, and let's see what you get for the tension now. That's 10 newtons. I guess I drew a very ugly 10. So, good luck, you guys. Free body diagram, some of the forces. I will walk around at a quarter protocol. Sure.
Color. Slowly, color.
Yeah, looking good. I think you guys are going to be okay on this. I checked last period, every single kid was doing it right. Let's see what they're doing. What you got?
Yeah. That's
Okay,
it.
5 divided by the cosine 75 is not that answer. So do it again. I think you've got Anaisa's problem with your calculator. Are you in radians or degrees? That's something horrible. Isn't it? Yes. Did you get 19?
Yeah, I did.
Calculators possessed by demons.
I can check the. I just.
So it's this
I
like
did.
a demon lights in there.
Oh, I put the.
What's that? No, 19 is correct. He got 5.7. Now it's 9, yeah, 19 is correct.
Thanks, friend.
Yeah. Cool.
Newtons?
All right.
Yeah.
Hey, you know what? I need to have enough time for the pulley stuff. So everyone I saw was doing a proper free body diagram, which makes me extremely happy. Everyone's getting their Y components and their X components. Y component, X component. Everybody's getting some of the forces in the Y direction equals MAY. So I got TY plus TY minus 10 equals 0. And of course, I think no one is surprised by the fact that no matter what the angle is, if it's symmetrical, then the Y component of each one of these tensions is going to have to be 5 newtons. That's no surprise. It's just because this angle is bigger, because it's a 75-degree angle, your T ends up being 5 newtons divided by the cosine of 75 degrees, which is equal to 19.3. Tell me, as that angle gets bigger and bigger, what's going to happen to the tension? Yeah, it's going to increase. It's going to get bigger and bigger because you have to somehow, and I'm going to demonstrate that for you now. You've got to somehow maintain the same, vertical component of tension while having a greater and greater horizontal component. Like, look at here, this is vertical, that's about 5. And then as I do this, do you see what's happening to the tension?
Yeah.
As that angle gets bigger and bigger, the tension gets bigger and bigger. And you know, if I had it almost horizontal, I could have a situation where a 10 Newton weight was creating 100 Newtons of tension if I have this thing, you know, horizontal enough. You see what I mean? As long as the vertical component remains 5, you just get bigger and bigger tension. Yeah. We'll talk more about this. Well, there's some conceptual problems that address this, and we'll talk about that when that comes. Okay, now it is time for me to talk about pulleys. There you go.
I'm gonna see. I don't get home until 8. 6. Okay, this is a pulley. The purpose of a pulley is for you to be able to exert a force in one direction and get a resultant force in a different direction. For example, if this were a refrigerator and people wanted to lift this refrigerator up to the 3rd floor, well, you couldn't get under the refrigerator and lift it to the 3rd floor because the 3rd floor is too high up. So you would rig up a pulley, and then you'd have a long rope, and then the men would pull down on the rope and thus pull the refrigerator upward. So it's a way for you to change the direction of your force. Another use of a pulley is if you use multiple pulleys, you can actually get a mechanical advantage, where now men could pull, and only men do this sort of work. I just want to let you guys know. Men would pull down, with 100 pounds of force and be able to lift something that's several hundred pounds because they would get a mechanical advantage. So that's a pulley. Well, right now we're just going to investigate one simple scenario, and that's a situation where you got a bunch of mass here and a bunch of mass here, and we want to know what it does. So here I've got 1,000 grams here. Right here I've got 700 grams. I've got 900 grams. I've got 950 grams. Okay, so I got 1,000 grams, 950 grams. Now, ordinarily, what should happen? Which direction should the 1,000 grams go? Down, and this guy should go up. But I let go and nothing's happening. Why not? Why isn't it moving? What's keeping this from moving? Shouldn't this guy go down? Why won't it go down? I mean, I can hit it, but,
Friction.
yeah, thank you very much, Leilani. Friction. A ideal pulley is massless and frictionless, but this is obviously not an ideal pulley. There's friction there, and friction is keeping this from doing it. Like, listen. But you hear that? That's friction. That's friction you're hearing, the squeaking, okay? So 950 versus 900, this is not going to fall. But what about 950 versus 1,000? I mean, it's not going to fall. But how about 900 grams versus 1,000 grams? Do you think this guy's going to fall now? Yeah. So you guys okay? And do you notice it falls pretty slow? 900 doesn't pull this guy down at a very big acceleration at all. Okay? But what if instead of 900, what if I made it 700? Now what would happen to the acceleration? It'd be faster, right? You guys okay with that? 700 is faster. And in fact, what if instead of 700, it was 500? Now what would happen to the acceleration? Really fast. Oh. Did I catch it? So you guys, and then of course, finally, what if it was 1,000 versus 0? Then what would acceleration be? Yeah, free fall would be 9.8. Okay, good. Well, I need to teach you how to deal with this simple type of pulley problem. And the key to it is going to be to make a free body diagram of both masses. So here we go. Suppose I have a pulley and I have 1 kilogram mass here and I have 2 kilogram mass here. And I want you to find the acceleration and the tension while it's accelerating. Acceleration and tension. Well, I'll tell you right now, the key to doing this problem is to make a free body diagram of both of the masses individually. So here they come. Here's the 1 kilogram mass. Here comes my free body diagram. I got tension up. I got the weight of that 1 kilogram mass, which is 9.8 newtons down. That's a free body diagram of this mass. Those are the only 2 forces it feels. Tell me, which direction is this guy accelerating, up or down?
Up.
You guys okay that it's accelerating upward? How do I know?
Because 2 is bigger than 1.
Yeah, because 2 is bigger than 1. But you're going to have to use your human intelligence. There's nothing about this drawing algebraically that's going to tell you this guy goes up. You're just going to have you use your common sense and go, this guy goes down and that guy goes up. That's the only way you're going to make that determination. So his acceleration is upward. I'll define up as positive. And so I do sum of the forces equals MA. So I got tension minus 9.8 newtons equals the mass, 1 kilogram, times A. And I'm going to solve for T, and I get 9.8 plus A. 1 equation, 2 unknowns. So you see why I'm going to have to do a free body diagram of the 2 kilogram guy, because I need a second equation with 2 unknowns, so I can solve them. So here comes the 2 kilogram guy. Tension up, 19.6 newtons of weight down. But which direction is this guy accelerating? Down. Is his acceleration going to be the same as that guy's acceleration? Well, yes it is, because they're connected by a string, right? I mean, they're not connected by taffy, where one guy can move and the other guy doesn't, right? Where just a taffy stretches. They're connected by a string. Whatever this guy does down, this guy has to do up. You see what I mean? They're connected. The length of the string is never changing. So the accelerations are going to be the same. So whatever this guy's acceleration is up, this guy's going to have the same acceleration down. Secondly, what about the tensions? Is the tension in this string going to be the same as the tension in that string? Well, I got to tell you, yes, it will. We assume that the string is on that pulley and the string doesn't slip, but we're assuming that the pulley itself is frictionless. You see? The string doesn't slip, but the pulley rotates without friction, we assume. Which means you can't have a difference of tensions. If you had a difference of tensions, then this guy would turn until the tensions were the same. So I get to use the same tension. I'm going to define up as positive, And so now I get to say sum of the forces equals MA. I got 10 minus 19.6 equals the mass 2 kilograms. But here's the weird thing. Here's what makes the pulley problem distinctive. What am I gonna have to put for this acceleration?
Negative
You guys getting negative 8? Because this A is pointing downward. This A is upward, so he gets to be positive. This A is downward, he is negative. The most common mistake students make on these pulley problems is they forget to put a negative A on that guy. So now I get to say T equals 19.6 equals 2A, negative 2A. Or T equals, oh wait, what am I doing?
Yeah.
Great. Now I've got two expressions for T, so I'm going to set them equal to each other. T, whoops. Oh, I'm feeling pressed for time, so now I'm making mistakes. 9.8 plus A equals 19.6 minus 2A, or 3A equals 9.8, or A equals 1/3 of G, 1/3 of 9.8, which ends up being about 3.27 meters per second squared. We've got about 5 minutes left, so I want to see if you can do a problem like this in the 5 minutes, and you're doing it, do it the same way. Here, give this a try. Pulley, frictionless pulley. This is 3 kilograms. This is 5 kilograms. Get me the acceleration. Oh, also, I could find the tension. Now that I know acceleration, I just plug into here, right? 9.8 plus 3.27, or my tension is approximately 13. Okay. But you've done that one, I just want you to get acceleration. Good luck. Do that problem now. So please do a free body diagram of the 3 kilogram and do a free body diagram of the 5 kilogram. And then it'll work out just swell. When you get to your 5 kilogram, is everybody making sure it's negative A when you do your 5 kilogram? Because the acceleration is downward, or they're finding out it's positive? Anyone getting 2.45? Yay. Yay. You should be getting 2.45 as an answer. But here's the last question I want to leave you with before you leave. Do you notice that the 1 and the 2 kilogram, you ended up getting 1/3 g as being the acceleration? The 3 and the 5, it ended up being 1/4. Can anyone figure out a kind of a shortcutty way that you could have got those answers really quick besides going through my process? Like, do you see a mathematical relationship between the fraction in front of g, the fraction in front of g, and the masses themselves? If you think of it by tomorrow, let me know. What do you think, Noel?
So on that one, the 1 kilogram plus the 2 kilogram is gonna equal 3 kilograms total. And the difference between the 1 kilogram and the 2 kilogram is the 1 kilogram, which is how you're getting there. And then I got
Yes.
stuck on this one for a second, but I figured it out. So
Tell
there's
me.
a total of 8 kilograms, and then the difference is 2, so that's how it's going.
Great, you guys okay? 2 out of 8, which is 1/4. That's it. Yeah, because the difference of the masses is what's accelerating it, but you're having to move the total amount of mass. Yeah, we'll talk about it tomorrow because the bell's gonna ring. Thanks a lot.